Right now, there are somewhere between 6 billion and 9 trillion planets in our galaxy alone that sit within the habitable zone of their stars. That is not a poetic estimate. That is a conservative lower bound derived from telescope data. And yet, as of this moment, we have confirmed life on exactly one of them. The question is not whether that seems improbable. It is. The real question is what that improbability actually tells us about the rest of the universe. To understand why scientists are increasingly convinced we are not alone and what that alien life might actually look like, we need to start not in space, but here, on Earth, with a surprisingly simple principle. Form follows function. Look at your own hand. 5 fingers, an opposable thumb. A grip evolved over millions of years to handle tools, to manipulate objects, to perform tasks requiring precision. Your eyes sit forward-facing on your skull, giving you stereoscopic depth perception, ideal for judging distances when you reach for something or move through complex terrain. Your brain, weighing roughly 1.5 kilograms, contains around 86 billion neurons, each one capable of connecting with thousands of others. You are, by any objective measure, an extraordinary piece of biological engineering. But here is the striking part. You did not have a designer. Every structure in your body exists because organisms that had it survived better than organisms that did not. And those survivors reproduced more, passing their traits on. Over millions of generations, random mutation and natural selection sculpted the human form from simpler precursors. Charles Darwin understood this when he voyaged through the Galapagos Islands in the 1830s and observed something deceptively ordinary: birds with different beaks. Finches on islands where hard seeds were abundant had thick, powerful beaks suited to cracking them open. Finches in environments rich with insects had slender, pointed beaks suited to probing crevices. The beak, in each case, matched the food source. Form followed function, and the mechanism behind it was evolution. What makes this relevant to the question of alien life is not Darwin himself, but a concept that emerged from his work: convergent evolution. Convergent evolution is the observation that completely unrelated lineages of life, facing similar environmental pressures, independently arrive at the same biological solutions. And the examples are everywhere. Vision evolved independently approximately 40 times on Earth. That is not 40 modifications to a shared ancestral eye. That is 40 completely separate lineages independently arriving at the same fundamental solution to the problem of navigating an environment flooded with light from a star. Eyes are such a good idea that life reinvented them again and again. If this has already caught your attention, consider subscribing, because we're just getting to the part most people never see. Now, let's continue. Wings appeared independently in insects, birds, bats, and the extinct pterosaurs. Bats are mammals. Birds descended from theropod dinosaurs. Pterosaurs were a separate lineage entirely. None of them inherited wings from a shared winged ancestor. Each lineage arrived at flight through independent paths. Form following function. Echolocation, the use of reflected sound waves to perceive the environment, evolved independently in bats and in dolphins. Both animals live in worlds where light is not the most reliable navigational tool. In bats, it is the darkness of night. In dolphins, it is murky water, different environments, identical solution. Photosynthesis, the biological capture of energy from starlight, has arisen dozens of times across completely unrelated lineages of microorganisms. Even koalas and humans, separated by hundreds of millions of years of evolution, have independently developed nearly identical fingerprint patterns because gripping textured surfaces requires the same structural adaptation regardless of the lineage doing the gripping. The implication of convergent evolution is profound. It suggests that when the environment poses the same problems, life converges on the same answers, not by design, not by coincidence, but because there are only so many efficient solutions to any given problem, and natural selection is very good at finding them. Now extend this logic beyond Earth. If there exist planets elsewhere in the universe with conditions similar to our own, and we now know there are many, then the same selective pressures would be acting on whatever life arose there. Light from a star would be present. Eyes would be a good idea. Tool use would confer an advantage. Something like hands or fingers would be favored. Complex problem-solving would allow an organism to outcompete rivals. A large brain, or whatever structure served the equivalent function, would be selected for. Bipedal locomotion, or some analogous efficient form of movement, might emerge because freeing the manipulative appendages for tool use is advantageous. This is why many scientists take seriously the possibility that intelligent aliens, if they exist, might look surprisingly humanoid. Not because humans are the template for all intelligent life in the universe, but because the template is the problem intelligent life needs to solve, and convergent evolution suggests the solutions might look similar. Of course, this only holds if the environment is similar, and across the universe environments vary enormously. On a planet with significantly lower gravity than Earth, the energy cost of pumping fluids through tall structures is reduced. Plants and animals alike might reach heights that would be impossible under stronger gravitational pull. Limbs could be longer, skeletons lighter, bodies more elongated. On a high-gravity world, the physics demand the opposite. Bones would need to be denser and more robust. Bodies would be shorter and more heavily built to withstand the increased downward force. It is even possible that on very high-gravity planets, complex life would be primarily aquatic, because water provides buoyancy that counteracts gravity, making large body sizes sustainable in a way they would not be on land. Distance from a star matters too. On a planet receiving less light than Earth, eyes would need to be larger to capture more photons. Pupils would be enormous. Or perhaps, as in the case of bats and dolphins on Earth, echolocation would become the dominant sense, with vision playing a secondary role. On a world with extreme seasonal variation, driven by a highly elliptical orbit, life might evolve extraordinary tolerance for temperature extremes. We already see this on Earth in organisms like tardigrades, microscopic animals capable of surviving the vacuum of space, intense radiation, and temperatures close to absolute zero by entering a state of near-suspended animation. On a planet where such extremes were the norm, this might become a common trait, not a rare one. Temperature also governs size in interesting ways. In the deep ocean trenches on Earth, where water is consistently cold, there is a phenomenon called deep-sea gigantism. Cold-blooded animals in cold environments can grow to enormous sizes because their metabolic rate slows and their lifespan extends. In hot desert environments, the opposite is often true. Smaller animals have a higher surface area relative to their mass, which allows them to dissipate heat more efficiently. Radiation exposure from a nearby or unusually active star would create entirely different evolutionary pressures. Around the heavily irradiated remains of the Chernobyl nuclear power plant, the pattern of which species thrive is striking. Dogs and other animals with rapid reproductive cycles, short lifespans, and high tolerance for genetic damage persist. Longer-lived organisms that accumulate radiation damage over decades struggle. A planet orbiting closer to an active star, or one without the protection of a strong magnetic field, might produce life forms with dramatically shorter natural lifespans, but faster reproduction and greater resistance to cellular damage from ionizing radiation. The principle in every case is the same. Form follows function. Life adapts to the conditions it finds itself in. The precise form that adaptation takes depends entirely on what the environment demands. And this logic does not stop at biology. It extends into culture, technology, and civilization. When European explorers encountered the civilizations of the Americas in the 15th and 16th centuries, they found societies at dramatically different technological levels, despite both sides being biologically identical humans. Historians have explored many reasons for this, including the availability and ease of domestication of local plant and animal species. Civilizations that could establish intensive, productive agriculture could free significant portions of their population from food production, allowing them to specialize in craft, science, engineering, and art. Civilizations forced to spend most of their labor on subsistence farming had less time available for other pursuits. The presence of easily accessible coal, timber, or other energy sources could spark industrial development. Deposits of iron, copper, tin, or rare earth elements could enable metalworking, electrical systems, or eventually computing. The absence of these resources could delay or prevent the same transitions. Environment shapes not just the bodies of organisms, but the trajectories of their civilizations. This brings us to a question that scientists have taken seriously since the 1960s. If intelligent civilizations are a natural outcome of evolution on suitable planets, and if the universe contains billions of suitable planets, how advanced might some of those civilizations be? And how would we detect them or avoid detection from them? In 1964, Soviet astrophysicist Nikolai Kardashev proposed a framework for classifying civilizations by their energy consumption. His logic was that the defining characteristic of technological advancement is the ability to harness energy. The more energy a civilization can access and use, the more it can build, explore, and communicate. A Type 1 civilization, by Kardashev's original definition, can fully harness all the energy available on its home planet. Every watt generated by geothermal activity, every joule of sunlight falling on the planetary surface, all of it captured and used. Humanity is not yet there. We currently sit at roughly 0.73 on this scale, meaning we use a substantial fraction of the energy available on Earth, but not all of it. A Type 2 civilization can harness the full energy output of its star. Our Sun emits approximately 380 septillion watts continuously. Capturing all of that would require engineering on a scale that seems almost mythological, structures large enough to encircle a star. The theoretical example is a Dyson sphere, a megastructure that surrounds a star and collects its entire energy output. No confirmed Dyson sphere has ever been found, though some stars have been examined with this possibility in mind after showing unusual dimming patterns. A Type 3 civilization can harness the energy of an entire galaxy. The Milky Way contains somewhere between 100 and 400 billion stars, each contributing its own energy output. A civilization operating at this scale would be detectably different from the background of space. We have seen no evidence of one. Since Kardashev, other scientists have extended the scale further. A Type 4 civilization would access the energy of the observable universe. A Type 5 would operate across multiple universes, if such things exist. And at the extreme theoretical limit, the Type Omega civilization would exist outside conventional space-time entirely, accessing forms of energy we have no framework to even conceptualize. Carl Sagan proposed a parallel classification system based not on energy consumption, but on information. How much unique knowledge does a civilization collectively possess? Sagan used an alphabetical scale, estimating that humanity in 1973 held roughly 10 to the power of 13 bits of unique information, placing us at approximately Type J. A hypothetical Type Z civilization would need to hold 10 to the power of 31 bits of information, which exceeds the total information content of the observable universe. Such a civilization, by Sagan's framework, would be essentially omniscient. These frameworks matter because they shape how we think about what we might find when we look outward. A civilization far ahead of us on the Kardashev scale would be detectable not by radio signals, which become incoherent over interstellar distances, but by the engineering signatures they leave on their environments: massive energy harvesting structures, unusual stellar spectra, atmospheric compositions that no natural process would create. And this brings us to the specific tools we are using right now to search for life beyond Earth. The Kepler Space Telescope, launched in 2009, monitored roughly 150,000 stars continuously, watching for the periodic dimming that occurs when a planet crosses in front of its star and blocks a small fraction of its light. This transit method is extraordinarily powerful. By measuring how much light is blocked and how frequently, scientists can determine a planet's size and its orbital period. From the orbital period and the star's mass, they can calculate the planet's distance from its star. From that distance and the star's temperature, they can assess whether liquid water could potentially exist on the planet's surface. The probability of detecting any given planet this way is actually quite low. It requires the planet's orbit to be aligned almost exactly edge-on relative to our line of sight. For a planet orbiting at roughly the same distance as Earth orbits the Sun, the probability of this alignment being favorable is less than 0.5%. For planets at greater distances, the probability drops further. This means that the planets Kepler detected represent a tiny fraction of the planets that actually exist within the stars it monitored. Taking this into account, scientists have estimated the total number of planets in our galaxy's habitable zone, the range of orbital distances where liquid water could exist on a planetary surface given the right conditions. Conservative estimates place this number at around 6.4 billion. Other estimates run significantly higher. Of the thousands of exoplanets that Kepler confirmed, 16 were classified as rocky, Earth-sized planets within their star's habitable zone. After filtering for factors like the type of star they orbit and whether they might be tidally locked, with one face permanently turned toward their star and the other in permanent darkness, roughly 4 emerged as credible candidates for Earth-like conditions. These 4 are Luyten b, Kepler 62f, Kepler 186f, and Kepler 442b. Our current technology cannot determine the composition of their atmospheres in any detail. That is a task currently underway with instruments like the James Webb Space Telescope. The way we study exoplanet atmospheres is through spectroscopy. When a planet transits its star, a small amount of the star's light passes through the planet's atmosphere. Different molecules absorb light at different wavelengths. By analyzing which wavelengths are absorbed, scientists can identify which gases are present in the atmosphere. Oxygen, water vapor, carbon dioxide, methane, and other compounds each leave a distinctive fingerprint. This is how we know Earth's atmosphere contains water and oxygen, because the spectral signature of our own planet looks exactly the way it should if you know what to look for. An inhabited planet would leave chemical signatures in its atmosphere that would be distinctive. The presence of both oxygen and methane simultaneously is particularly intriguing because the two gases react with each other quickly. For both to be present at the same time, something must be continuously producing them. On Earth, that something is life. Oxygen comes from photosynthetic organisms. Methane comes from biological decomposition and from the metabolic processes of microbes. A planet showing both gases in its spectrum would be a powerful indicator of biological activity. Some scientists have also pointed out that the presence of industrial pollution in an atmosphere, the equivalent of what our own civilization pumps into the air, would be detectable at interstellar distances. A planet with unusual concentrations of certain artificial chemicals could be a sign not just of life, but of technologically advanced life. We have not yet found such a signature on any confirmed exoplanet, but we are only beginning to look with instruments sensitive enough to try. The search for extraterrestrial intelligence has a different approach. Rather than looking for atmospheric chemistry, it listens for deliberate or incidental broadcasts across the electromagnetic spectrum. Frank Drake formalized this in 1961 with what became known as the Drake equation. It is not really an equation that gives a precise answer. It is a framework for organizing our uncertainty. The equation asks, how many communicating civilizations should currently exist in our galaxy? To find out, you multiply together several factors. The rate at which suitable stars form, estimated at around 5 per year in our galaxy. The fraction of those stars that have planets, which Kepler data suggests is close to 1, meaning nearly every star has at least one planet. The number of potentially habitable planets per star system, estimated conservatively at around 0.3% of all planets. The fraction of habitable planets where life actually arises. The fraction of life-bearing planets where intelligence emerges. The fraction of intelligent species that develop technology capable of broadcasting detectable signals. And finally, the average lifespan of a communicating civilization. The first 3 values can be estimated with reasonable confidence from telescope data. The last 4 remain deeply uncertain, and the range of plausible values is staggering. If life arises easily on habitable worlds, and 1% of estimates suggest it does, because on Earth it appeared almost as soon as conditions allowed, then the fraction of habitable planets with life might be close to 1. But if life required a specific, extraordinarily unlikely set of chemical accidents to get started, the fraction might be vanishingly small. We have exactly one data point, Earth. And from a single data point, it is impossible to distinguish between these 2 possibilities. The same uncertainty applies to intelligence. Earth has produced millions of species. Only one developed technology capable of communicating beyond its planet. Is that because intelligence is rare, a near miraculous exception to the general pattern? Or is it because of the particular history of our planet, the asteroid that wiped out the non-avian dinosaurs 66 million years ago, clearing ecological space for mammals to diversify, the specific climate fluctuations of the Pleistocene that may have driven rapid brain development in our lineage? If the dinosaurs had survived, would intelligence have eventually appeared in them? If intelligence is almost inevitable given enough time, the Drake equation produces very different answers than if it requires a chain of specific lucky accidents. When scientists have run the numbers with pessimistic assumptions about how easily life and intelligence arise, the answer comes back at or near 0. Under those assumptions, we might be the only communicating civilization in the galaxy right now, or one of a very small number. When they run it with optimistic assumptions, where life is common and intelligence is a natural endpoint of evolution on suitable worlds, and civilizations last for long periods, the answer rises dramatically. 9 civilizations under moderate assumptions, 900 in slightly more optimistic scenarios, and if civilizations regularly achieve a kind of long-term stability, lasting for hundreds of millions or billions of years, the number could be in the millions, all within our galaxy alone. The universe contains somewhere in the range of 2 trillion galaxies, each containing hundreds of billions of stars. Even if habitable planets were extraordinarily rare, occurring only once per million star systems, the total number across the observable universe would still be in the hundreds of millions. The scale of the universe is itself an argument for the existence of life beyond Earth, which creates a problem. If intelligent life might be common, why have we not heard from anyone? This is the Fermi Paradox, named after physicist Enrico Fermi, who reportedly asked the question at a lunch in 1950. If the galaxy is old enough, and if intelligent life arises reasonably often, then some civilizations should have had billions of years to develop, expand, and spread. Even without faster-than-light travel, a civilization expanding at a fraction of the speed of light could colonize the entire Milky Way galaxy within tens of millions of years. The galaxy is around 13 billion years old. There has been ample time, so where is everyone? Several answers have been proposed. Some are bleak, some are stranger than fiction. The dark forest theory proposes that intelligent civilizations exist but do not communicate, because revealing your location in a universe containing potentially aggressive competitors is dangerous. Any civilization that broadcasts its existence is gambling that none of the civilizations that receive the signal have the means and the motivation to destroy them. Given the potential consequences, the rational strategy might be silence. Like hunters moving quietly through a dark forest where other hunters might also be present, civilizations that survived long enough to become technologically capable would have learned not to announce themselves. There is a physics-based reason why this threat is so serious. You do not need soldiers or warships to destroy a civilization. You only need mass moving at a sufficient fraction of the speed of light. An asteroid-sized object, accelerated to a significant fraction of light speed, and directed at a planet, would deliver an energy release far exceeding any nuclear arsenal. The planet it struck would not see it coming, because the object would be traveling so fast that the light from it would barely precede its arrival. Defensive systems dependent on early warning would be useless. This is not science fiction speculation, it is straightforward physics. Any civilization advanced enough to cross interstellar distances would also understand this. Another possibility is indifference. A civilization thousands or millions of years ahead of us technologically would perceive us the way we perceive insects. Not with hostility, but with complete disinterest. We do not broadcast to beetles. We do not attempt communication with bacteria in the soil. The gap in comprehension is too large. An advanced civilization might be perfectly aware of our existence and simply find us beneath the threshold of interesting. A more optimistic possibility, one that several scientists have argued is actually consistent with the long-term trend of civilizations on Earth, is that advanced civilizations trend toward cooperation. The history of human civilization, for all its violence, shows a gradual scaling upward of the units of cooperation. Bands became tribes. Tribes became chiefdoms. Chiefdoms became kingdoms. Kingdoms merged into nations. Nations formed alliances. The trend, irregular and not guaranteed, has been toward larger cooperative units over time. Technology has driven this, because increasingly powerful weapons make large-scale violent conflict increasingly suicidal, and increasingly powerful communications make distant cooperation increasingly practical. Extended to a much older civilization, this trend might produce something like a genuinely cooperative interstellar community, and a community at that level might choose not to contact younger, more volatile civilizations. For the same reason, an experienced diplomat might choose not to hand a child a loaded weapon. Not out of cruelty, but out of caution. The younger civilization has not yet demonstrated that it can be trusted with the knowledge and technology that contact would bring. The biology of any alien civilization, whatever it looks like, would also be shaped by the history of its development. Organisms that compete for resources develop competitive traits, but the ones that survive long enough to become intelligent typically do so partly through cooperation. Wolves hunt in packs. Primates form social hierarchies. Humans build institutions. Cooperation within groups has been a consistent feature of the most successful species on Earth. Any intelligent species would likely show something similar, having navigated the same tension between individual competition and collective coordination. What drives all of this is energy. Life requires energy. Metabolism is the biological extraction of usable energy from the environment. Every adaptation, every behavior, every piece of technology is ultimately about acquiring and using energy more effectively. And this is why the Kardashev Scale is actually a more fundamental description of civilization than any cultural or political category. It measures the thing that defines what a civilization can do. Understanding how life arises in the first place requires going back much further than civilization. It requires going back to chemistry. The Earth formed approximately 4.5 billion years ago. The Moon formed shortly afterward, probably from the debris of a massive collision between the proto-Earth and another planetary body. By 4.4 billion years ago, liquid oceans existed, and by 4.3 billion years ago, possibly as early as that, the first evidence of life appears in the geological record. Life appeared on Earth astonishingly quickly after conditions allowed for it. Within 200 million years of the oceans forming, something was already alive. This rapidity is itself an argument. If life required a long chain of specific unlikely accidents, we would not expect it to appear almost as soon as conditions permitted. The speed suggests that the chemistry leading to life is not improbable. It suggests that given the right conditions, it may be close to inevitable. The chemistry that underlies life on Earth is not exotic. The basic molecular building blocks, fatty acids, amino acids, and nucleotides, have been found in meteorites. They form in space. They are delivered to planetary surfaces by asteroid and comet impacts. They are not rare ingredients. They are common ones. Fatty acids are the molecules that form cell membranes. They have a distinctive structure, with one end that is attracted to water and one end that repels it. When fatty acids are placed in water, they spontaneously arrange themselves into spherical bilayer structures, with the water-repelling tails pointing inward and the water-attracting heads pointing outward. These structures are called liposomes. They form without any biological machinery. They are a purely physical consequence of molecular geometry and the properties of water. And they look remarkably like primitive cells. They can encapsulate other molecules. They can divide. They can concentrate chemical reactions within their interior. Amino acids are the building blocks of proteins. 20 different amino acids, in various combinations and sequences, produce the entire range of proteins that drive every biological process. Proteins are enzymes that catalyze chemical reactions. They are structural components of cells. They are signaling molecules. They are the tools of biology. Nucleotides are the building blocks of RNA and DNA. RNA is of particular interest in the study of life's origins because it serves two functions that are normally separate in modern cells. It can carry genetic information, like DNA, and it can catalyze chemical reactions, like a protein enzyme. This dual functionality suggests that RNA may have been the molecule at the center of life's earliest chemistry before the more specialized DNA and protein system evolved. The second law of thermodynamics states that entropy, the disorder of a closed system, always increases over time. Life seems at first glance to violate this. Cells are extraordinarily ordered. The information content of a single human genome is immense. How does such order arise from the chaos of chemistry? The answer is that life is not a closed system. It imports energy from its environment, uses that energy to build ordered structures, and exports waste heat, increasing the total entropy of the universe even while creating local pockets of order. Erwin Schrödinger captured this in his 1944 book, What is Life?, observing that living organisms feed on negative entropy from their environment. Jeremy England, a physicist at MIT, has gone further, arguing that systems exposed to sustained energy gradients will naturally evolve toward states that dissipate that energy more effectively. Life, under this view, is not an improbable accident. It is a predictable consequence of the laws of thermodynamics acting on chemistry in the presence of energy. The early Earth provided exactly this kind of energy gradient. The planet's surface was in chemical disequilibrium with its interior. The young ocean was acidic and electron-poor. The subsurface mantle was alkaline and electron-rich. Where these two regions met, at hydrothermal vents on the ocean floor, there were sustained chemical gradients that drove reactions. Similar gradients exist wherever volcanic activity meets water, in deep sea vents, in coastal hot springs, in volcanic pools. Scientists believe the first life emerged from one of these environments, harnessing the chemical energy at the interface between the oxidized ocean and the reduced rock below. The transition from chemistry to biology did not require a designer. It did not require a miracle. It required the right molecules, the right energy source, and enough time for natural selection to begin acting on replicating systems. Once a molecule or set of molecules could make copies of themselves, and once those copies could vary slightly, and once those variations affected survival, Darwinian evolution took over. The rest is the history of every living thing that has ever existed. On Earth, the jump from single-cell to multicellular life took an astonishing length of time, about 1.5 billion years. The difficulty of coordinating cells, getting individual units to cooperate and differentiate into specialized tissues, turns out to be genuinely hard. Multicellular life is not just more cells. It is cells that communicate, divide labor, and sacrifice themselves for the whole. Achieving that level of coordination required enormous amounts of evolutionary experimentation. The jump to intelligence required more experimentation still. Of the hundreds of millions of species that have existed on Earth, only one developed the combination of traits that allowed for language, cumulative culture, tool use, and abstract reasoning. Whether this makes intelligence rare in the universe, or whether it simply reflects the particular contingencies of our planet's history, remains an open question. What we can say is this: the chemistry of life is universal. The same elements that make up your body are present throughout the universe: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. They are among the most abundant elements produced by stellar nucleosynthesis. They are present in every molecular cloud from which stars and planetary systems form. The molecules they form are equally universal. The moons of the outer planets in our own solar system provide reason to think that life-supporting chemistry is not limited to Earth-like environments. Enceladus, one of Saturn's moons, has a subsurface ocean beneath its icy crust. Water-rich plumes erupt from its southern pole, carrying with them the chemical signatures of hydrothermal activity from the seafloor beneath. The conditions at those vents, warm water, chemical gradients, mineral surfaces, are strikingly similar to the environment scientists believe gave rise to life on Earth. Europa, a moon of Jupiter, has a similar subsurface ocean, with a liquid water layer likely twice the volume of all Earth's oceans. Titan, also orbiting Saturn, has lakes and rivers, but of liquid methane rather than water, raising the question of whether an entirely different biochemistry might be possible. On Mars, liquid water once flowed freely across the surface. The planet has extensive river valleys, ancient lake beds, and minerals that form only in the presence of water. Something changed in Mars's history, probably the loss of its magnetic field and much of its atmosphere, that converted it from a potentially habitable world to the cold, dry, irradiated environment it is today. But liquid water persisted longer than we once thought, perhaps long enough for life to have gotten started. The Perseverance rover is currently examining ancient lake sediments in the Jezero crater, looking for biosignatures that might indicate past microbial life. The question of whether we are alone in the universe is, at its core, a question about the conditions required for life to arise and how frequently those conditions are met. Every discovery about the prevalence of planets, the chemistry of life, the energy gradients that drive biological emergence, and the range of environments where life can persist, moves us toward a more informed estimate. None of these discoveries has provided direct evidence of extraterrestrial life, but many of them have shifted the plausibility calculation in the direction of life being widespread. The number we still need most urgently is the fraction of habitable planets where life actually arises. If that fraction is close to 1, as the rapid emergence of life on Earth might suggest, then the galaxy almost certainly contains vast numbers of living worlds. If that fraction is extremely small, even if the galaxy contains billions of habitable worlds, we might still be extraordinarily rare or even unique. Everything depends on this one number, and we cannot determine it from a sample of one. The next decade of space exploration is likely to be the most consequential in the history of the search for life. The James Webb Space Telescope is already beginning to characterize the atmospheres of known exoplanets with unprecedented sensitivity. Future missions targeting nearby Earth-like worlds may be able to detect biosignature gases in their spectra. Missions to Europa and Enceladus could, in principle, find living organisms in the water plumes erupting from their surfaces. Mars sample return missions may bring back rocks containing preserved evidence of ancient microbial life. And if any of these missions find what they are looking for, it will not just answer a scientific question. It will fundamentally change how we understand our place in the universe. A second independent origin of life, anywhere in the solar system or beyond, would transform life from an apparent miracle of one into a universal phenomenon. It would mean that wherever conditions allow, life arises. It would mean that the vast universe is almost certainly teeming with it. The silence we currently hear from the cosmos is not proof of emptiness. Radio signals become indistinguishable from background noise within a few light years of their source. Even our own civilization would be essentially undetectable at interstellar distances if you didn't know exactly where to look and what to look for. The universe has been emitting radio signals for over 13 billion years, and we have been listening for perhaps 60 of them. The absence of a signal in 60 years of listening to a tiny fraction of the sky, using methods that might not be effective for detecting civilizations very different from our own, is not strong evidence. What we do know is that the universe contains the right ingredients for life everywhere we look. The chemistry is universal. The physics that drives biological self-organization appears to be a natural consequence of thermodynamics. The number of potentially habitable worlds is staggering, and the history of life on Earth suggests that once chemistry starts working in the right direction, it moves quickly. Whether there are minds elsewhere in this universe looking back at the same sky we look up at, wondering the same questions we wonder, remains the most extraordinary open question in science. The answer may come within our lifetimes. The tools we have built are, for the first time in history, capable of finding it. And whatever that answer turns out to be, it will reshape everything we thought we understood about where we came from and what we are. If you find these questions as compelling as the science behind them, the research ongoing across exoplanet studies, astrobiology, and space exploration is worth following closely. This is one of the few moments in history where the most fundamental questions humanity has ever asked are becoming answerable. Stay curious. Let us go deeper into what biology actually tells us about the likelihood of intelligence, because this is where the argument becomes more nuanced and more surprising. Intelligence, as we experience it, is not a single trait. It is a cluster of capabilities that evolved independently and were then woven together over millions of years of primate evolution. These capabilities include working memory, the ability to hold and manipulate information in mind across short time spans, Planning, the ability to model future states of the world and evaluate the consequences of different actions. Theory of mind, the capacity to model the mental states of other individuals and predict their behavior. Language, the ability to encode complex, arbitrary information in external symbols that can be shared between individuals and transmitted across generations. Cumulative culture, the ability to build knowledge incrementally, where each generation starts from the accumulated knowledge of the previous one rather than beginning from scratch. Every one of these capabilities has analogues, partial versions, or proto-forms in other species. Chimpanzees, orangutans, and gorillas show rudimentary theory of mind. Crows and ravens plan for future states, caching food in locations they will return to days later. Dolphins have demonstrated self-recognition in mirrors, which is considered an indicator of self-awareness. Elephants show what appears to be grief over the deaths of their companions. Octopuses can solve novel puzzles that require planning and spatial reasoning, despite having a radically different nervous system architecture from vertebrates, with more than half of their neurons distributed throughout their arms rather than centralized in a brain. The fact that so many different lineages independently evolved partial versions of the cognitive toolkit associated with intelligence suggests that intelligence is not a freakish accident. It is a direction that natural selection explores repeatedly. The full package, the combination of all these capabilities in a form powerful enough to produce technology, language, and civilization, appears to have happened only once in the history of life on Earth, in our lineage, after the last common ancestor we share with chimpanzees, roughly 6 to 7 million years ago. But that may tell us less about the rarity of intelligence than it seems. Complex traits generally evolve only once, even when they are evolutionarily accessible, because once one lineage succeeds, the ecological space that would have supported a second lineage is already occupied. When humans evolved full cognitive capability, we rapidly outcompeted every other hominin species, including the Neanderthals, the Denisovans, and several other lineages that were coexisting with us until relatively recently. A second independently evolving intelligent species on Earth would have had to compete directly with us, and our technological and social advantages would have made that extremely difficult. The absence of a second intelligent species on Earth may tell us more about the competitive dynamics after intelligence arises than about how rare the initial transition is. Consider what the fossil record actually shows. The hominin lineage shows a consistent trend toward increasing brain size and cognitive complexity over millions of years. Our ancestors 2 million years ago had brains roughly half the size of ours. By 1 million years ago, brain size had increased substantially. The trend is not a random walk, it is directional. Something was consistently selecting for larger, more complex brains across several different hominin species. The most plausible explanations involve social competition within groups, where individuals with better cognitive abilities to navigate social dynamics, predict rivals' behavior, and form strategic alliances had significantly higher reproductive success, and environmental variability, where the fluctuating climate of the Pleistocene repeatedly drove selection for cognitive flexibility over behavioral rigidity. If these selective pressures are common features of the environments that complex life inhabits on other worlds, then the trend toward intelligence might not be unique to Earth. It might be a predictable outcome of evolution in environments with significant variability and social complexity. Now consider what happens after intelligence appears. The transition from intelligent organisms to technological civilization involves another set of critical transitions, each of which represents a potential filter on the path to a communicating species. Language is one such transition. Without language, cumulative culture is impossible. You can observe and imitate as many animals do, but you cannot efficiently encode and transmit complex abstract information. Every generation essentially starts from scratch. With language, knowledge becomes cumulative. A discovery made by one person in one generation becomes available to everyone in the next. This is the engine that makes technological civilization possible, and it may have been one of the most significant transitions in the history of life on Earth. Writing takes this further. Spoken language is limited to the geographical range and lifespan of the individuals who know it. Written language persists independently of any individual. It can be copied, distributed, and transmitted across vast distances and long time spans. The invention of writing approximately 5,000 years ago marks the beginning of what we might call the information accumulation phase of human civilization, when knowledge began to compound across generations far more effectively than before. Once writing and complex language exist, the speed of technological development increases dramatically. The printing press in the 15th century accelerated this further by reducing the cost of duplicating and distributing information. The Internet has accelerated it again by essentially eliminating the cost of distribution entirely and allowing global synchronization of knowledge in near real time. If this trend is extrapolated, and there is no obvious reason why it should stop, the rate of technological development should continue to accelerate. The practical implication is that civilizations that survive long enough should reach capabilities that look almost unimaginable from our current vantage point within a time frame that is short by cosmic standards. This is relevant to our search for extraterrestrial intelligence because it suggests that the gap between a civilization at our level and one that has been developing for even a few thousand years longer than us could be almost incomprehensible. A civilization that began its technological development only 10,000 years before us, a tiny fraction of a blink in cosmic time, might be so far ahead of us that the comparison becomes meaningless. Their science, their technology, their understanding of physics might bear no more resemblance to ours than our science bears to that of a bacterium. The question then becomes not whether they exist, but whether they would be detectable by anything we know how to look for. And here we encounter one of the most honest admissions in the search for extraterrestrial intelligence. We might not know what we are looking for. Our searches have been overwhelmingly focused on radio waves, because radio is what we use. But a civilization thousands of years ahead of us might have moved to communication methods we have not yet discovered or that we do not know how to detect. They might communicate via quantum entanglement or neutrino beams or some physical phenomenon we have no theoretical framework for. The absence of a detectable radio signal from space does not mean the absence of civilization. It may mean that advanced civilizations do not use radio for communication between star systems, any more than we still use semaphore flags to communicate between continents. Let us also consider one of the most sobering aspects of the Drake equation, the last term, the average lifespan of a communicating civilization. We have no data on this whatsoever. We do not know how long our own civilization will last, and we are the only example we have. The threats to civilization are real and varied. Nuclear weapons have existed for less than a century, and we have so far avoided using them in warfare since 1945. But the weapons still exist, and the systems that control them are imperfect. Climate change poses long-term risks to agricultural systems and habitability of large regions of the planet. The development of biotechnology means that the ability to engineer pathogens with pandemic potential will eventually be widely accessible. And asteroid impacts, while rare, are a persistent statistical threat over timescales of millions of years. On the optimistic side, the same technology that creates these risks also creates the means to mitigate them. We can build systems to detect incoming asteroids and deflect them. We can develop clean energy technologies that eliminate the climate risks of fossil fuels. we can develop monitoring and response systems for pandemic threats. And most importantly, if we can establish a permanent presence beyond Earth, even the catastrophic destruction of our home planet would not mean the extinction of our species. The long-term survival of a civilization may depend critically on whether it can transition from a single planet species to a multi-planetary one before it destroys itself. This transition is happening right now, in the early stages, with the development of reusable rockets and serious planning for crewed missions to Mars. If we succeed, we become orders of magnitude more resilient to existential threats. If enough civilizations make this transition, the galaxy may be populated with civilizations that have been spreading and surviving for billions of years. The detectability of these civilizations would depend entirely on what they chose to do. A civilization that expanded aggressively, building megastructures, redirecting the energy of stars, and reshaping planetary environments would leave unmistakable signs visible across galactic distances. A civilization that chose, for whatever reason, to live quietly in balance with its environment, consuming only what it needed and maintaining a small technological footprint, might be nearly invisible even to instruments far more sensitive than ours. The range of possible civilizational choices is as wide as the range of choices human cultures have made. Some human cultures have been expansionist and resource-hungry. Others have developed philosophies of minimal footprint and coexistence with nature. Some have been aggressive, others have been peaceful. Any alien civilization would face the same range of choices, and the ones that survived long enough to become truly advanced would have had to navigate the same existential risks we face. There is a particular scenario that several scientists have found compelling when thinking about why we might not yet see evidence of galactic civilization. Known as the Great Filter, it proposes that there is some extremely unlikely transition on the path from simple chemistry to a galaxy-colonizing civilization. The question is where that filter sits. If it is behind us, in the past, perhaps in the transition from chemistry to biology, or from single-celled to multicellular life, or from animal intelligence to full technological civilization, then we may have already passed through the hardest part. This would be good news. It would suggest that while intelligent civilizations are rare, there is nothing preventing us from eventually becoming a long-lived interstellar species. If the Great Filter is ahead of us, if there is something that consistently destroys civilizations after they reach our technological level, then our future is considerably grimmer. The fact that we see no obvious evidence of galactic-scale civilization, despite the universe being old enough that such civilizations should have had billions of years to develop, could be interpreted as evidence that most civilizations that reach our level do not survive much longer. The existence of multiple independent great filters, small ones, spread across the path from chemistry to galaxy-colonizing civilization could also explain the apparent absence of visible alien civilizations without requiring any single catastrophic bottleneck. If each of dozens of necessary transitions has only a small probability, the cumulative probability of completing all of them could still be extremely small, even if no single transition is vanishingly improbable. The most scientifically productive thing we can do is to keep searching and to keep refining our estimates of each of the terms in the Drake equation. Every confirmed Earth-like planet in a habitable zone narrows our uncertainty about the frequency of potentially habitable worlds. Every spectroscopic analysis of an exoplanet atmosphere improves our ability to identify biosignatures. Every sample returned from Mars or future mission to Enceladus or Europa directly tests whether life arose anywhere else in our solar system. If we find microbial life on Mars or Enceladus, even simple single-celled organisms, that discovery would be the most significant in the history of science. It would tell us that life arose independently at least twice within our own solar system. This would strongly imply that life is common throughout the universe, because our solar system is not obviously special in any way that would make it uniquely hospitable. If we do not find life anywhere in our solar system despite extensive searching, that would not prove we are alone. It would simply confirm that life is at least not abundant in our immediate neighborhood, which could reflect many things, including our particular location in the galaxy, the particular history of our solar system, or the real rarity of life, even in environments that seem broadly habitable. The truth is that we are doing science at the absolute frontier of human knowledge. We are asking questions that no previous generation had the tools to even begin answering. And the tools we are building now, more powerful telescopes, more sensitive spectrographs, robots that can sample subsurface environments, are moving us closer to answers that previous generations could only speculate about. The philosophical implications of finding life elsewhere would be as profound as the scientific ones. Every major human cultural and religious tradition was developed in a world where Earth was understood to be the center of things, whether literally or metaphorically. The discovery that we are one of potentially billions of life-bearing worlds would require a fundamental re-examination of how we understand our place in the universe. This is not a reason to avoid searching. It is a reason the search matters so much. The physicist Enrico Fermi's question, "Where is everyone?" remains unanswered. But it is less puzzling than it was when he asked it, because we now understand how vast the universe is and how limited our detection capabilities are. We have been listening for about 60 years with instruments designed to detect a very narrow range of possible signals, pointing at a tiny fraction of the sky, looking for patterns that an alien civilization might happen to produce in a way that matches our expectations. The silence so far is not evidence of absence, it is evidence that the search has barely begun. What would it actually mean, practically, to receive a confirmed signal from an extraterrestrial intelligence? The first challenge would be decoding it. Physicists and linguists have proposed various approaches, based on the assumption that mathematics is universal because physical law is universal. A civilization that knows physics could communicate in the language of mathematics. Prime numbers, for example, are a mathematical concept that would be recognizable to any civilization advanced enough to build a transmitter. The SETI community has also explored how information theory might guide decoding, since any deliberate signal would presumably be structured to maximize information content in a recognizable way. The second challenge would be responding, which raises its own complex questions. Given the vast distances involved, any communication would have multi-century or multi-millennium round-trip delays. Meaningful dialogue in any conventional sense would be impossible. But even a one-way transmission, a message from another world telling us they exist and what they know, would be transformative. Imagine having access to the accumulated knowledge of a civilization that has been studying the universe for 1,000,000 years longer than we have. The third challenge would be the social and political implications of the discovery. Who speaks for Earth? Who decides how to respond? What would the existence of a technologically superior civilization, even one at an enormous distance, mean for human social structures, religions, and political systems? These are not questions science can answer. They are questions for all of humanity to work through, and ideally to work through before we have to answer them under time pressure. For now, what is clear is that the universe does not prohibit life elsewhere. The physics allows it. The chemistry enables it. The number of suitable worlds is enormous. The only thing we lack is the direct evidence, and the search for that evidence is accelerating. In the meantime, the scientific questions remain some of the most exciting ever posed. How does chemistry become biology? How does biology become intelligence? How does intelligence become civilization? How does civilization survive itself? And how many times, across how many worlds, has this sequence of events played out in the 14 billion year history of the universe? We do not yet know, but we are asking the questions with better tools than any generation before us, and the answers, when they come, will be worth the wait. One of the most underappreciated aspects of the search for extraterrestrial life is the extent to which our own biology constrains our imagination about what life can be. We define life, as we noted earlier, by the properties of the life we know: self-sustaining chemical systems that metabolize, reproduce, and evolve. But this definition is drawn entirely from a single example, and that example is built on a very specific biochemistry. All life on Earth uses water as its primary solvent. The unique properties of water, its ability to dissolve a vast range of substances, its capacity to moderate temperature, its tendency to remain liquid across a wide range of temperatures, make it extraordinarily useful for biology. But water is not the only possible solvent for chemical reactions. Ammonia, for instance, becomes liquid at temperatures well below water's freezing point, and it can dissolve a range of organic and inorganic compounds. A life form built around liquid ammonia as its solvent could potentially exist on a planet too cold to support water-based life. Liquid methane, as we find in the lakes of Titan, is another candidate. The conditions on Titan are profoundly hostile to Earth life. The surface temperature is around -170 degrees Celsius. Water is as hard as rock there, but liquid methane flows, and some scientists have speculated that cell membranes built from nitrogen-containing molecules, acrylonitrile specifically, could form spontaneously in liquid methane, creating the structural basis for chemistry in that environment. Whether any metabolism could take place at such low temperatures is a serious question, because chemical reaction rates decrease dramatically with temperature, but the laws of chemistry do not categorically exclude it. Even more exotic possibilities have been proposed. Silicon is in the same chemical group as carbon and can form long-chain polymers, but it does so much less readily, and silicon-oxygen bonds are generally much more stable than silicon-carbon bonds, which could make silicon-based chemistry less flexible. In extremely high-temperature environments, however, silicon chemistry might be more viable than it is at Earth temperatures. A silicon-based life form in a high-temperature environment is not physically impossible, merely unfamiliar. The concept of life based on pure energy, without any physical substrate, has also been explored in theoretical physics. Exotic quantum field configurations, plasma-based self-organizing systems, or information processing structures in electromagnetic fields have been proposed, though none with a concrete biological mechanism. These remain in the domain of speculation, but the fact that they cannot be ruled out by any known physical law is itself significant. For practical purposes, the most productive approach to the search for life is to start with what we know works and search for it. Water-based, carbon-based life leaves chemical signatures we know how to look for. If we find it, we can expand our search. If we do not, we can consider what our absence of detection tells us about the constraints on life. The role of chance in the specific trajectory of life on Earth is worth considering seriously. The mass extinction 66 million years ago, caused by an asteroid impact that struck the Yucatan Peninsula with the energy of roughly 1 billion nuclear weapons, eliminated approximately 3/4 of all species on Earth, including all non-avian dinosaurs. Before that impact, dinosaurs had dominated land-based ecosystems for about 165 million years. Mammals had existed for a similar amount of time, but remained small, mostly nocturnal, and ecologically marginal, constrained by the dominance of large dinosaurs. After the impact, with the large dinosaurs gone, mammals rapidly diversified to fill the ecological niches that had opened. Within a few million years, the mammalian radiation produced the lineages that would eventually give rise to whales, bats, horses, elephants, and primates. Without that impact, it is quite possible that dinosaurs would still dominate Earth, and that something like intelligence, if it emerged at all, would have emerged in a very different lineage. Some paleontologists have speculated about what might have happened if the non-avian dinosaurs had survived and continued evolving. Some lineages showed trends toward increasing brain size and bipedalism. Given another 100 million years of evolution, might some dinosaur lineage have eventually developed technology? The point is not that the specific outcome on Earth was inevitable, but that the underlying processes, natural selection operating on diverse, competing lineages in a changing environment, consistently produce increasing complexity, behavioral flexibility, and in some lineages, increasing cognitive capability. The specific path depends on the specific history of impacts, climate changes, volcanic events, and ecological dynamics on a given planet. But the underlying dynamics that drive complexity upward may be broadly applicable wherever complex chemistry and stable energy sources coincide. Another consideration that rarely appears in popular discussions of the search for extraterrestrial intelligence is time. Specifically, the question of when in the history of the universe intelligent life is likely to arise. The universe is approximately 13.8 billion years old. The first generation of stars formed within a few 100 million years of the Big Bang, but they were made almost entirely of hydrogen and helium, the only elements produced in significant quantities by the Big Bang itself. Carbon, nitrogen, oxygen, phosphorus, and all the other elements heavier than helium are produced inside stars by nuclear fusion. When massive stars end their lives in supernova explosions, they scatter these heavy elements into the surrounding space, where they mix with gas clouds and eventually become incorporated into the next generation of stars and planets. This means that planetary systems with the chemical complexity needed for life could not form until the universe had produced and recycled at least one generation of stars. The first planets with Earth-like chemical compositions probably formed around 8 to 10 billion years ago. Earth itself formed 4.5 billion years ago, about 2/3 of the way through the current age of the universe. We are not at the beginning of the story, we are somewhere in the middle. Stars like our Sun, with lifetimes of around 10 billion years, are common. Stars that are somewhat smaller and less luminous, known as red dwarf stars, are far more common, making up roughly 3/4 of all stars in the galaxy. Red dwarfs live for tens to hundreds of billions of years, far longer than the current age of the universe. If life can arise around red dwarfs, which remain uncertain due to the potentially intense stellar flares and radiation environments of young red dwarfs, then the universe has barely begun its history of producing potentially habitable environments. From this perspective, if life and intelligence are common outcomes of suitable conditions, then we might be among the earliest intelligent civilizations in the universe, not in the sense of being first by a long margin, but in the sense that we are living at a time before most of the universe's eventual story has played out. The vast majority of potentially habitable planets that will ever exist may not yet exist. The question of alien civilizations may be less about who is out there now, and more about a universe that is just beginning to produce the conditions for the rise of mind. This changes the implications of the Fermi Paradox somewhat. If we are indeed in an early phase of galactic civilization, then the absence of evidence for galaxy-spanning civilizations might simply reflect the fact that not enough time has passed. The galaxy is 13 billion years old, but the conditions for complex life have only been truly favorable for perhaps 8 billion years, and the development of technological civilization requires billions of years of biological evolution before it can begin. On this timescale, we might be early, not unique, and the absence of older civilizations could simply reflect the youth of the universe in civilizational terms. Consider what our own galaxy might look like in 10 billion years, if we survive and continue to develop. If we manage to avoid extinction and gradually expand our presence in space, even at a very conservative rate of expansion, the descendants of Earth's civilization could have reached every star system in the Milky Way within 1 billion years. We would be the very ancient alien civilization that a young civilization in the far future would be asking about. We would be the ones who might seem absent or incomprehensible to those younger minds, simply because the scale of what we had become would be so far beyond their frame of reference. This reversal of perspective is genuinely useful. When we ask why we do not hear from advanced civilizations, we are implicitly assuming that advanced civilizations should be doing something we can detect. But there is no particular reason why that should be true. The things a civilization does when it is young and resource-limited, broadcasting radio waves, building large physical infrastructure, expanding rapidly, may not be what a civilization does when it is mature, stable, and has had billions of years to optimize its relationship with its environment. The long-term trajectory of any surviving technological civilization might involve a transition toward efficiency and sustainability rather than continuous exponential growth. Infinite growth on a finite energy budget is not physically possible. Every civilization that survives long enough must eventually find a stable equilibrium with its environment. A civilization in that equilibrium state might be extraordinarily advanced in terms of knowledge, creativity, and experience, while maintaining a much smaller energy footprint than a civilization in the aggressive expansion phase. Such a civilization might be nearly invisible from outside. Its energy consumption would be modest. Its communications might be narrow beam, targeted, and encrypted. It might choose not to broadcast, having learned that broadcasting attracts attention that can be unpredictable. It might exist in ways that leave no obvious signature in the electromagnetic spectrum. This does not mean we should stop searching. It means we should think more creatively about what we are searching for. The most convincing biosignatures might not be radio waves. They might be subtle chemical imbalances in a planet's atmosphere, or faint infrared excesses suggesting energy collection, or the absence of expected astronomical objects indicating they have been moved or dismantled. Some scientists have proposed looking for megastructures, artificial objects large enough to be visible at interstellar distances. Others have proposed looking for laser pulses, because laser communication is more energy efficient than radio for long-distance signaling and might be a preferred technology for advanced civilizations. The search space is enormous. We are looking for a signal in a universe containing hundreds of billions of galaxies, each containing hundreds of billions of stars, across a range of possible signal types, with instruments that can only examine a tiny fraction of the sky at any given time, using methods that might not be suited to the signals actually being sent. The fact that we have not yet found anything is, under these circumstances, not very informative. What we need most is better technology and more systematic coverage. The breakthrough. Listen Initiative, launched in 2015, is the most comprehensive SETI search ever conducted, covering 10 times more sky than any previous search and scanning a much wider range of radio frequencies. Future radio telescope arrays, such as the Square Kilometre Array being built in South Africa and Australia, will be thousands of times more sensitive than existing instruments. Optical SETI programs are searching for laser pulses across wide fields of sky, and space-based telescopes are progressively improving our ability to study exoplanet atmospheres. These efforts are happening now, in real time, funded by a combination of government agencies and private philanthropists who have decided that this is one of the most important scientific questions we can ask. The chance that any individual year will produce the discovery we are hoping for is small. The chance that the cumulative progress of these programs over the coming decades will fundamentally change our knowledge of whether we are alone is much higher. In the meantime, the question remains open, and there is something intellectually honest and important about sitting with an open question. Science at its best is not about confident proclamations. It is about following evidence wherever it leads, maintaining uncertainty where uncertainty is warranted, and continuing to ask questions that previous generations could not answer. Are we alone? We do not know. Is life common in the universe? We do not know. Is intelligence a rare or frequent outcome of evolution? We do not know. These admissions of ignorance are not failures. They are the honest starting point for a search that may eventually produce the most transformative answer in the history of human inquiry. What we do know is this: the universe is made of the same atoms everywhere. The laws of physics and chemistry are universal. The conditions that gave rise to life on Earth, liquid water, chemical energy gradients, complex organic molecules, stable temperatures, are not exotic or unusual from a cosmic perspective. They are the kinds of conditions that should arise on enormous numbers of worlds throughout the universe. And the history of life on Earth shows that once those conditions exist, the chemistry of life moves quickly to exploit them. The probability that we are the only result of all of this, the single solitary instance of mind arising from matter in a universe of 2 trillion galaxies, is not zero. But it is the kind of claim that requires extraordinary evidence, and we do not have that evidence. What we have instead is the consistent experience that the universe is far richer, far more complex, and far more capable of surprising us than any previous generation imagined. Every time we have looked more carefully at the universe, we have found it more hospitable to complexity than we expected. We have found planets around nearly every star we have examined carefully. We have found organic molecules in interstellar space, in meteorites, in comets. We have found liquid water on moons that had no right to have it. We have found life in places on Earth, deep in ice, in boiling acid, in rocks kilometers underground, where no one expected it to be. The universe, it seems, is not trying to prevent life. It is providing the ingredients and the conditions repeatedly and generously, and allowing chemistry and physics to do what they apparently do naturally when given the chance. Whether life has taken that chance elsewhere, and whether any of it has been watching the same stars we watch, asking the same questions we ask, we do not yet know. But the question is more alive than it has ever been, and the search continues. Let us take a closer look at the specific worlds in our solar system that scientists consider the most promising candidates for life beyond Earth, because the details matter enormously, and the details are more interesting than most people realize. Mars is the obvious starting point. It is the planet most like Earth in our solar system, with a day that lasts 24 hours and 37 minutes. Polar ice caps, seasons caused by axial tilt, and a surface geology that records billions of years of planetary history. Ancient river valleys carve the southern highlands. Enormous lake systems once filled impact craters. The Jezero crater, where the Perseverance rover landed in February 2021, is the remnant of a lake that held liquid water for potentially millions of years, fed by a river delta whose sediments are now being analyzed in extraordinary detail. The problem with Mars is not that it lacks water, it is that it lost the conditions that kept water liquid on its surface. Mars has a weak magnetic field today, a remnant of what was once a much stronger one generated by its molten iron core. When that dynamo stopped, possibly between 3 and 4 billion years ago, the planet lost its magnetic shield against the solar wind. The solar wind, a constant stream of charged particles from the sun, slowly stripped away the Martian atmosphere. As the atmosphere thinned, the greenhouse effect that had kept Mars warm enough for liquid water diminished. temperatures fell, the surface water froze or was lost to space. The planet became the cold, dry, irradiated environment we know today. But life, if it arose during the warm, wet, early period of Mars, might not have disappeared when the surface became hostile. It might have retreated underground. The Martian subsurface still has liquid water, we are now fairly confident. Briny reservoirs detected by radar instruments beneath the South Polar ice cap in 2018 suggest liquid water exists today, kept liquid by dissolved salts that lower its freezing point. Similar subsurface liquid environments might exist elsewhere on Mars, and subsurface environments are shielded from the intense radiation that sterilizes the Martian surface, which receives ultraviolet and cosmic radiation levels that would be lethal to most life on Earth. If Martian life ever existed, and if any of it survived by retreating underground, it would likely be microbial, living in rock pores and accessing energy from chemical reactions between water and rock, the same kind of lithotrophic metabolism we find in bacteria kilometers underground on Earth. We cannot currently access these deep environments with our rovers. Future missions, including sample return missions that will bring Martian rock cores back to Earth for analysis in laboratories far more capable than anything we can land on Mars, may give us a definitive answer about whether Mars ever hosted life. Europa is perhaps an even more intriguing target. This moon of Jupiter, roughly the size of our own moon, is covered in a shell of ice that floats on a global ocean of liquid water. The ocean is kept liquid not by sunlight, which barely reaches Jupiter's distance from the Sun, but by tidal heating. Europa orbits Jupiter in a gravitational tug-of-war with two other large moons, Ganymede and Io. The gravitational flexing caused by this orbital resonance heats Europa's interior, maintaining liquid water beneath a frozen crust that may be between 15 and 25 kilometers thick. The floor of Europa's ocean is likely rocky, and tidal heating would drive hydrothermal activity there, creating the same kind of mineral-rich, chemically energetic environment at the boundary between water and rock that scientists believe gave rise to life on Earth. Europa's ocean has been liquid for potentially billions of years, long enough for complex chemistry to develop, even if the pace is slow. The Europa Clipper mission, launched in 2024, is en route to Jupiter and will conduct dozens of close flybys of Europa, analyzing its surface composition and searching for signs of chemistry that might indicate active biology. A future lander mission that could penetrate the ice and sample the ocean beneath would be far more definitive, but the engineering challenges of drilling through 20+ kilometers of ice in a remote environment with no possibility of repair make that a long-term aspiration. Enceladus, the sixth largest moon of Saturn, has made itself even more accessible to study than Europa, because it is actively venting its interior ocean into space. Geysers of water vapor and ice particles erupt from cracks near the South Pole, creating a plume that extends thousands of kilometers into space and feeds material into one of Saturn's rings. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through this plume multiple times and detected a remarkable chemistry: water, sodium, potassium, carbon dioxide, methane, molecular hydrogen, and complex organic molecules, including compounds that on Earth are produced by living organisms processing carbon. The molecular hydrogen is particularly significant. It is produced when hot water reacts with rock in a process called serpentinization, the same process that occurs at hydrothermal vents on Earth's ocean floor. And serpentinization vents on Earth are ecosystems. They host communities of bacteria and archaea that live entirely on chemical energy, with no sunlight involved at any step. The hydrogen and methane released by the venting reaction is food for these microbes. If something similar is happening at the base of Enceladus's ocean, The same energy source would be available there. The tentative detection of phosphorus-containing compounds in the Enceladus plume, reported in 2023, added another piece to the puzzle. Phosphorus is an essential element for all known life, forming the backbone of DNA and RNA and the central energy currency molecule of biology, adenosine triphosphate. Finding phosphorus in an extraterrestrial ocean significantly strengthens the case for Enceladus as a potentially habitable environment. Titan is the most alien candidate. Saturn's largest moon has a dense atmosphere of nitrogen and methane, surface pressure about 1.5 times Earth's at sea level, lakes and rivers of liquid methane and ethane, rain cycles of methane rather than water, and surface temperatures around -179 degrees Celsius. In almost every superficial respect, Titan is a world designed to kill life as we know it. But Titan also has something extraordinary. It is a vast natural laboratory in which the chemistry that may have preceded life on Earth, the synthesis of complex organic molecules from simpler ones under the influence of ultraviolet radiation, is happening continuously at a planetary scale right now. Titan's atmosphere is rich with organic chemistry. The orange haze that gives the moon its distinctive color is made of complex hydrocarbon molecules, tholins, produced when sunlight breaks apart nitrogen and methane, and the resulting fragments recombine in complex ways. These tholins, when they settle to the surface and come into contact with water, have been shown in laboratory experiments to spontaneously produce amino acids and nucleobases. On Titan, the tholins are not in contact with liquid water on the surface. But Titan has occasional episodes of cryovolcanism, where water from the subsurface briefly erupts onto the surface. During these events, tholins and water come into contact. The reactions are brief, perhaps lasting only thousands of years before the water refreezes, but even brief windows of prebiotic chemistry have been proposed as potentially significant. The Dragonfly mission, a rotorcraft lander developed by NASA, is scheduled to arrive at Titan in the 2030s. It will explore multiple sites on Titan's surface, analyzing the chemistry of tholins and searching for biosignatures, chemicals that would indicate that biological processes have occurred or are occurring. The results of that mission will tell us something profound about where prebiotic chemistry naturally leads, given enough time and the right conditions. All of these missions, Perseverance on Mars, Europa Clipper at Jupiter, Dragonfly at Titan, represent the beginning of a systematic survey of our solar system for life beyond Earth. For the first time in history, we are looking for life not just with thought experiments and equations, but with physical instruments operating in the environments where life might actually be found. The results of the next few decades of exploration will dramatically reduce our uncertainty about whether life in the solar system requires Earth or whether it is more widely distributed. Now let us go back to the fundamental question of what life actually is and what chemistry tells us about its likelihood. Because the more we understand about the origin of life on Earth, the more the conditions we are looking for elsewhere come into focus. The earliest unambiguous evidence of life on Earth is found in rocks from the Pilbara region of Western Australia, around 3.5 billion years old. These rocks contain microfossils, preserved remnants of microbial mats, communities of bacteria that lived at the surface of shallow seas. But chemical evidence, including carbon isotope ratios that reflect biological processing of carbon dioxide, suggests life may have existed even earlier, potentially as far back as 4.1 billion years ago, within the first few hundred million years of Earth's history. This extraordinary speed of life's emergence after Earth's formation has been the subject of intense scientific debate. One school of thought holds that it demonstrates life is easy, given the right conditions. Life happens quickly because the underlying chemistry is driven by thermodynamics to produce it. Another holds that the early emergence of life on Earth could be a sampling bias. We are here to ask the question because life arose on Earth. If we had access to millions of planets with conditions similar to early Earth, we might find that life arose on only a few % of them, but that every inhabited planet would show early emergence, because planetary histories long enough for observers to evolve require early starts. This reasoning is called the anthropic principle in its weak form. It is a legitimate consideration, but not a fully satisfying answer. What we need is not philosophical reasoning, but empirical data, which means finding other examples of life arising independently or confirming its absence after careful search. The chemistry of the origin of life has been experimentally explored since Stanley Miller and Harold Urey demonstrated in 1953 that organic molecules, including amino acids, form spontaneously when gases believed to be present in Earth's early atmosphere are exposed to electrical discharges simulating lightning. The Miller-Urey experiment was revolutionary because it showed that the building blocks of life are not exotic or difficult to produce. They arise naturally from simple ingredients under conditions that would have been common on the early Earth. Since then, the field has progressed enormously. Scientists have demonstrated the spontaneous formation of RNA nucleotides from simpler precursors under conditions plausible for the early Earth. They have shown that short RNA strands can catalyze their own replication, at least weakly. They have demonstrated that cell-like vesicles made from fatty acids can divide and grow while encapsulating RNA. They have identified plausible energy sources, including proton gradients across the alkaline vents of the ocean floor, that could have driven the synthesis of the first organic polymers without needing any previously existing biological machinery. None of these individual demonstrations proves how life actually originated. But together, they paint a picture in which the transition from chemistry to biology, while complex, involves no mysterious or physically impossible steps. Every transition that has been studied in detail has turned out to have a plausible natural mechanism. The picture that is emerging is one in which life is less a miracle and more a consequence, a natural destination of chemistry given enough time, the right ingredients, and a sustained energy source. The concept of autocatalysis is central to this picture. An autocatalytic reaction is one in which the products of the reaction catalyze the reaction itself, causing it to accelerate over time. Autocatalytic chemical systems are self-amplifying. Given sufficient raw materials, they can grow exponentially. And when multiple autocatalytic systems compete for the same raw materials, the one with the faster or more efficient cycle wins. This is a form of chemical selection, a precursor to Darwinian selection operating at the molecular level before any molecule capable of storing heritable information existed. The theoretical biologist Stuart Kauffman has argued that networks of mutually autocatalytic molecules, sets where each molecule catalyzes the production of another molecule in the set, can spontaneously arise in sufficiently complex chemical mixtures. Once such a network forms, it self-organizes and self-amplifies, drawing in resources and growing at the expense of less organized chemistry around it. Kauffman calls these autocatalytic sets, and their spontaneous formation represents a plausible first step in the origin of life, a kind of proto-metabolism that precedes and potentially enables the emergence of genetic information. The emergence of genetic information, the ability to store and transmit heritable sequences that encode functional properties, is the other key transition. Modern life uses DNA to store information and RNA to express it, with proteins doing the actual work of catalysis and structure. But this system is circular in a chicken and egg way. DNA needs proteins to replicate itself, and proteins need DNA to be made. This circularity is broken by the RNA world hypothesis, which proposes that early life used RNA for both functions Since RNA can carry sequence information like DNA and catalyze reactions like proteins, over time the system became divided into specialists, with DNA taking over long-term information storage and proteins taking over catalysis, with RNA as the intermediary. Evidence for the RNA world hypothesis includes the fact that the core machinery of protein synthesis, the ribosome, is fundamentally made of RNA with proteins added later as structural supports. The catalytic activity of the ribosome resides in its RNA components, not its protein components. The ribosome is an RNA machine that makes proteins, which suggests it is a relic of a time when RNA did everything. This is one of the most compelling pieces of evidence that the RNA world hypothesis is not merely speculative, but reflects actual evolutionary history. The question of how the first RNA sequences arose is one of the most active areas of research in the field. Short RNA chains can form spontaneously from nucleotide building blocks, particularly on mineral surfaces that concentrate and orient the molecules. Mineral surfaces, particularly clays and certain iron-sulfur minerals, have been proposed as scaffolds where early RNA could have formed and been protected from degradation. The pores of hydrothermal vent minerals could have served as compartments, concentrating molecules and facilitating reactions that would not occur in open solution. The interplay between all of these elements, fatty acid vesicles providing compartmentalization, mineral surfaces facilitating RNA synthesis, autocatalytic chemical networks providing protometabolism, and RNA sequences encoding functional chemistry, creates a picture of the origin of life as an emergent process rather than a designed one. Each component evolved to work with the others through the same process that drives evolution today: differential survival and replication. The systems that worked better survived and reproduced. The ones that worked less well disappeared. This picture is not yet complete. There are significant gaps in our understanding of how these components came together in the right sequence and the right environment. But the picture is far more detailed and far more plausible than it was 50 years ago, and the rate of progress in the field continues to accelerate. Every year, new experiments demonstrate new plausible pathways, new chemical reactions, new conditions under which the building blocks of life form spontaneously. The emerging consensus in the scientific community, not universally held but increasingly supported by evidence, is that the origin of life is a hard problem but not an impossible one. Given the right conditions, the chemistry of life may be a natural outcome of physical law. If this is correct, and the conditions required are not extraordinarily rare, then life should be widespread in the universe. The ingredients are everywhere. The energy sources are common. The physics and chemistry are universal. The only remaining question is whether the specific sequence of events that led to the first living cell requires conditions so narrow and specific that they arise only rarely, or whether the path to life is robust, with many possible routes that converge on the same destination. We do not yet know, but we are closer to knowing than any previous generation, and the tools we are building will carry us closer still. In the meantime, the universe waits, vast and ancient and full of the same atoms that make up every cell of your body, scattered across 2 trillion galaxies and 14 billion years of cosmic history, potentially full of life, certainly full of the ingredients for it. Whether mind has arisen elsewhere to wonder about its own existence is the question that defines this moment in the history of science, and it is a question we are finally, seriously, beginning to answer. The history of human thinking about life beyond Earth is itself a remarkable story, one that tracks alongside the development of science itself. For most of human history, the question was not taken seriously as an empirical one. It was philosophical or theological. The ancient Greeks debated whether other worlds existed and whether they might be inhabited, but without any means of answering the question through observation or experiment. The invention of the telescope in the early 17th century changed everything. Galileo pointed his instrument at the moon and saw mountains and valleys, a surface that looked geological, not divine. He looked at Jupiter and saw moons orbiting it, demonstrating that Earth was not the unique center around which all celestial bodies revolved. The universe was suddenly revealed as a physical place, operating by physical laws, and the question of whether other physical places might host life became a scientific rather than purely philosophical one. The astronomer Christian Huygens, writing in the late 17th century, argued systematically that the stars were suns like our own sun, that they were likely to have planets orbiting them, and that those planets might well be inhabited. His reasoning was based on analogy and the principle of mediocrity, the idea that Earth and its sun should not be assumed to be uniquely special in a universe that appeared to operate by consistent laws. His arguments were not scientifically testable at the time, but they were logically coherent, and they established a framework for thinking about extraterrestrial life that has remained influential. The 19th century saw a surge of popular speculation about life on other planets, particularly Mars. The Italian astronomer Giovanni Schiaparelli observed linear features on Mars in 1877 and called them canali, meaning channels. This was mistranslated into English as canals, implying artificial construction. The American astronomer Percival Lowell became obsessed with the idea that Mars was inhabited by an intelligent civilization that had built a global system of canals to transport water from the polar ice caps to the equatorial deserts. He built an observatory dedicated to the study of Mars and wrote extensively about Martian civilization. Lowell's ideas were controversial even in his time, and subsequent observations showed that the canals were optical illusions, artifacts of the limits of 19th century telescopes and the tendency of the human visual system to perceive linear patterns in ambiguous data. But his work helped establish public interest in the search for extraterrestrial life that persists to this day. The 20th century brought increasingly precise observations and the sobering realization that Mars was far more hostile to life than Lowell had imagined. The Mariner 4 spacecraft, which flew past Mars in 1965, returned the first close-up images of the Martian surface, a barren, crater-pocked landscape with a thin, cold atmosphere. Later missions confirmed that the surface was bombarded by ultraviolet radiation, that liquid water could not exist stably at the current atmospheric pressure, and that the planet was thoroughly inhospitable to surface life as we know it. But the Viking landers in 1976 conducted the first direct test for life on another world. They scooped up Martian soil and ran 4 experiments designed to detect biological activity. One experiment, the labeled release experiment, produced a positive result that has been debated ever since. A small amount of carbon dioxide was released when water was added to the Martian soil in the presence of radioactive nutrients, suggesting that something in the soil was metabolizing the nutrients. But the other experiments did not support the presence of life, and the consensus interpretation was that the result was caused by oxidizing chemistry in the Martian soil rather than biology. This interpretation may have been premature. Recent analysis suggests that the Viking results are consistent with what you would expect from soil containing perchlorate salts, highly oxidizing compounds that are now known to be abundant in Martian soil. Perchlorate would destroy organic molecules during the high-temperature analysis used by the Viking instruments, which might explain why organics were not detected even if they were present. The labeled release result might have been caused by perchlorates reacting with the water added, not by biological metabolism, but it might also have been caused by both, with biological signatures masked by the chemical background. The question of what Viking actually found remains technically unresolved, and it serves as a reminder of how difficult it is to design an unambiguous test for life in an environment we do not fully understand. Life on Mars, if it exists or existed, might use chemistry we have not anticipated, leaving signals we have not been trained to recognize. This epistemological challenge, how do you search for something when you do not know exactly what you are looking for, is one of the deepest problems in astrobiology. The definition of life we use is inevitably shaped by the life we know. Our biosignatures are the chemical signatures of Earth life. Our assumptions about what life needs are based on what Earth life needs. Any life that departed significantly from the Earth pattern might not match our expectations in ways that make it undetectable, or worse, detectable but misidentified as chemistry. Scientists working on the origin of life have begun to propose a more fundamental definition of life that might transcend the specific biochemistry of Earth. Life as a process of self-sustaining chemistry that undergoes Darwinian evolution. This definition does not specify what the chemistry must be, only that it must be capable of replication, variation, and selection. By this definition, an RNA world precursor to modern cells would qualify as life, as would a silicon-based replicator or a methane metabolizing organism in liquid methane, provided the underlying chemistry supports heritable variation and selection. The challenge with this broader definition is that it is harder to detect remotely. Chemical imbalances that indicate biological activity are detectable in planetary atmospheres. But the presence of a replicating, evolving chemistry in a subsurface ocean is much harder to confirm from a spacecraft. It requires direct sampling and detailed chemical analysis, which is why missions that can physically access the environments in question are so scientifically valuable. The long-term strategy of astrobiology is thus necessarily multi-pronged. Remote sensing from Earth-based and space-based telescopes can identify candidate planets with potentially biological atmospheric chemistry. Robotic missions to nearby bodies can access environments directly and perform detailed chemical analysis. And eventually, crewed missions to Mars and robotic missions to the oceans of Europa and Enceladus can conduct the kind of thorough, adaptive search that has the best chance of actually finding life if it is there. The timeline for this search is measured in decades to centuries, not years. Building the technology to access Europa's ocean, for example, requires solving engineering problems that have not yet been solved. Drilling through tens of kilometers of ice with no possibility of human intervention, operating in a radiation environment intense enough to damage electronics, and analyzing samples in situ with instruments sensitive enough to detect chemistry at very low concentrations. These are hard problems, but they are engineering problems, not fundamental physical barriers. With sustained investment and effort, they are solvable. The investment required is large by the standards of individual scientific projects, but modest by the standards of what humanity spends on other priorities. The entire budget of NASA for all of its missions and programs combined is approximately $25 billion per year, a fraction of a percent of the United States federal budget. The astrobiological component of that is a small fraction again. The scientific return on that investment, in terms of new knowledge and transformative discoveries, has been extraordinary by any reasonable measure. The deeper question, beyond funding and technology, is one of priority. How much does it matter whether we are alone in the universe? The answer to that question depends on who you ask. For scientists, the discovery of even microbial life elsewhere would be the most significant scientific result in history. It would fundamentally change biology, chemistry, and our understanding of the conditions required for life to arise. It would have profound implications for the probability of complex life and intelligence elsewhere in the universe. And it would, inescapably, change the way humanity understands itself. For philosophers and theologians, the implications would be equally profound. Every major tradition of human thought has grappled with the question of human uniqueness and human purpose. The discovery that life is widespread in the universe would require those traditions to expand their frameworks in ways that some would find liberating and others would find disorienting. For ordinary people, the discovery would likely be experienced differently depending on how it came. The discovery of a simple microbe in Martian rock might be received with scientific excitement, but relatively little personal impact on daily life. The discovery of a signal from an intelligent civilization, however, would be impossible to process quietly. It would mean that there are minds elsewhere, that thought and experience are not confined to Earth, that the universe is inhabited in a way that makes our own existence feel both less lonely and less certain. The philosopher Nick Bostrom has argued, counterintuitively, that finding microbial life on Mars would actually be bad news for humanity in a specific sense. If simple life is common throughout the universe, then the Great Filter, whatever barrier stops most civilizations from becoming galaxy-spanning, is probably ahead of us rather than behind us. But if Mars is sterile despite having been potentially habitable for billions of years, it suggests the transition from chemistry to biology is so difficult that it rarely happens, and that our existence is the result of beating extraordinarily long odds. Under this scenario, the Great Filter is behind us, and we might have a relatively clear path ahead. This is a genuinely thought-provoking argument, even if it is not universally accepted. The absence of life on Mars would not prove that life is rare throughout the universe, since Mars is a very specific environment and its history is not typical. But it would provide evidence that the transition from chemistry to life is not as easy as the rapid emergence on Earth might suggest. And that evidence would be scientifically significant, even if philosophically it would not carry the emotional weight of actually finding life. The search for extraterrestrial life, ultimately, is a search for context. It is an attempt to understand Earth and life on Earth not as isolated phenomena, but as instances of something that either does or does not happen throughout the universe. If life is common, Earth is one node in a vast network of living worlds, each shaped by its own history, each following its own evolutionary trajectory, each potentially having reached stages of development we have not yet imagined. If life is rare, Earth is something close to unique, and the responsibility of being the custodians of the only known living world in a vast, mostly empty universe carries a weight that is almost incomprehensible. Either way, the search is worth pursuing. Either answer would be among the most significant pieces of knowledge humanity has ever acquired. And the process of searching, the development of new technologies, the systematic exploration of our solar system, the characterization of thousands of exoplanet atmospheres is itself producing scientific returns that justify the effort regardless of the ultimate result. We stand at a unique moment. For the first time in the 14 billion-year history of the universe, or at least for the first time that we know of, a species has developed the capability to ask whether it is alone and the tools to begin answering that question empirically. Whether the answer is yes or no, the asking matters. The curiosity that drives the question is itself one of the most remarkable things that has ever happened in this universe. A small cluster of atoms on a rocky world, orbiting an ordinary star in the outer spiral arm of an average galaxy, looking outward and wondering whether, somewhere out there, something else is wondering too. Keep watching the sky.